I'm Anil Kumar, and in this particular video, we have kind of a different approach to understand possible graphs of rational functions. Now, when we say rational functions, we are trying to say that it is of the form of r of x, which is a ratio of two polynomials, and I prefer to use numerator and denominator of these polynomials with n of x and d of x, and of course d of x is not equal to 0. That is the restriction for our rational functions. Now, what kind of graphs can we have? Now, to begin with, we can assume that the denominator is equals to 1. In that case, all polynomial graphs, do you understand? So all polynomial graphs are rational function graphs to begin with. So many times when I talk to students, I believe they understand that polynomials are not rational functions. So that is a myth. So we could have all kinds of graphs of polynomials. All these are possible rational function graphs, okay? So you could have like this, or you could have a graph kind of like this, right? So all these graphs are possible rational function graphs where the denominator is 1. So that is one case. And then we also talk about numerator being 1, right? So that is also interesting. If numerator is 1, we normally refer to them as reciprocal functions, correct? So reciprocal functions, what you will notice normally is that their graphs is 1 over x kind. We say 1 over x, if the denominator is x, will be, for example, f of x equals to 1 over x. So that becomes the parent function for us, and the graph of 1 over x is kind of like this. Now this graph introduces us to two different concepts which we have not seen in polynomial functions, and these are about the asymptotes, right? So we say we have a horizontal asymptote, right? This is horizontal asymptote. Horizontal asymptote is where the graph approaches, but it is never there when x is approaching positive or negative infinity. And then we have vertical asymptote, right? So we also have vertical asymptote, right? Vertical asymptote is the value which x is trying to reach, but it never reaches, correct? So these are the two very important concepts which we learn while exploring rational functions. Equation for horizontal asymptote is always y equals to something. In this particular case, it is y equals to 0. Since y is trying to approach 0. Vertical asymptote, however, is what x is trying to approach. X is trying to approach 0, and that is the equation for vertical asymptote. I've also seen this kind of mistake being happening. They just interchange x and y, right? So x-axis equation is y equals to 0. Please do remember that. Now let's look into some of the types of graphs which the rational functions can have, right? So there is no limit to their graphs. As you can see, we could have denominator as 1, we could have numerator as 1, and those are the things. Second, of course, these functions can be transformed, right? So once you transform these functions, then what happened? You could have different vertical and horizontal asymptotes, but the nature of the graph remains same. That is what it means. It could be translated left or right, up or down, or it could be dilated, right? Stretched or compressed horizontally or vertically, but the nature of the graph remains same, and that is very important. This is the basic nature for the rational function, right? Now that is what we're trying to understand here. Then in rational functions, at times we can have graphs which are kind of straight lines, not just curves. For example, we can have a graph like this, but this may have a twist, a hole here, kind of like this. A straight line with a hole. So that is another kind of discontinuity. What we already saw here is a discontinuity because of vertical asymptote. X is trying to reach 1 over x, right? It cannot be equal to 0, so x is not equal to 0. So that gives you restrictions on the domain, which you expect on most of the rational functions. Now in this particular case, let us say we have a line with a hole that represents a rational function. If let us say this point is 1, and let's take this point as 2, right? In that case, actually, I can write down the equation of this line, right? So the equation of this line could be, let's say g of x is equal to, we have a whole at 1. It means there is a factor which cancels out, and that factor is x minus 1, and it should be divided by x minus 1. So that is the factor for the whole. But after it cancels out, what remains is a line. That is how we have to see this function. What remains is the line. So what remains is this line with y-intercept of 2, right? And slope, let's assume 1 for simplicity. So we'll say x plus 2. So that becomes an equation of this rational function. So it is x minus 1 times x plus 2 divided by x minus 1. Now this video also helps you to correlate the graph with the equation. Let me give you one more equation and try to write down the equation of this function on your own once you see my diagram. Okay, so in this case I will consider a parabola. Okay, let me take an inverted parabola this time. So kind of like this. Okay, but giving a twist to this parabola, I will make a hole somewhere. Okay, let this be the hole on the y-intercept itself. Okay, that's very interesting. I never thought about it, but just made it up. Okay, now to give the equation for you, let me give very simple points, and let's say this point for us is minus 2, this point is plus 3 for us. Okay, now this is your rational function. How will you write equation of this rational function? Obviously, it is kind of a parabola. It is left after you divide by something, and that divisor created a hole. Do you see that part? So we can say, well, here the function could be, let me write h of x as the function this time. So what is the whole position? It is at x equals to 0. So the factor which really got cancelled out was x. Correct? So x got cancelled out, and that gives us a restriction that the function cannot have x equals to 0, and therefore we have a hole here at x equals to 0. But after it cancels out, what are you left with? Well, after it cancels out, we are left with a parabola whose equation is, since it is coming downwards, let me begin with minus. Okay, we can write something a later, but minus, you could write 1, that is good enough. But these are two x-intercepts, so the family will be x plus 2 times x minus 3, correct? So that gives you the equation of this particular rational function. So we could have rational functions with holes, and that is another kind of important discontinuity which you'll find in rational functions. So the discontinuity hole is very important, and as you see, we have a common factor. So that is because of common factor in n of x and d of x. Do you see that? So that results into a rational function which will have a graph like I've shown, right? So it could be any polynomial for that matter, correct? So we have these polynomials with these kinds of discontinuities, right? So these are some good examples which you could think about, and then we will also consider one other type of a polynomial, and I should say the rational function ratio of polynomials. Where we will talk this time about oblique asymptote. That's another thing which we have learned so far. So this is the oblique asymptote. Let me write down here oblique asymptote. Okay, this doesn't work now. Oblique asymptote. Okay. So oblique asymptote is when the rational function's graph is trying to approach somehow the value of a line, correct? That is where we get into oblique asymptotes. So the graph of such a function could be kind of like this. For example, it's just trying to approach it, right? And we have a vertical asymptote along this side, correct? So it could be like this. It could be like this also, right? So a graph very different from what you have seen so far. So those are also the graphs of your rational functions. Now the question here is, How do I write equation for this graph? Okay, so here let us say the function is m of x and we are trying to approach a line. Let us say this y-intercept is 5 for us. Okay, in that case, and let us assume a simple slope of 1. Okay, let us make it 2 this time. So it will be 2 of x and the y-intercept of 5. Good job. So that becomes the equation of the line. Well, this is the equation of the line which this function is trying to approach, but it is never there. You get the point. What you will notice is slightly more than that. It is slightly more than that. That means we can add something to it, correct? So to be very simple, we can add some number. Let's say we add 0 to it. Why did I add x? Since we also have a vertical asymptote, and here x cannot be 0, right? So x equals to 0 is my vertical asymptote. So x should be there in the denominator. So this function m of x, which is 2x plus 5 plus 1 over x, represents the graph of rational function which I have drawn there. Do you get the point? The idea is, if x is very, very large, then 1 over x is small and m of x approaches the line. So if x is approaching infinity, let's say positive infinity, in that case 1 over x approaches 0 and m of x approaches the line 2x plus 5. Do you get the point? So that is the whole concept. So we could have rational functions which are approaching a line, right? Similarly, you could also have, now that's a thinking problem and I'll leave it here now. I will not extend it further. Sometimes we say that the rational function is approaching a parabola. Okay, that is kind of saying that the graph of this function is, let me make a similar graph here, but this time it is not going like this, but it is kind of like this. Okay, and let's say this is a vertical asymptote, correct? And here somehow it just turns and well, I'm not sure how it should be, but it could be like this. Do you understand? So what is really happening here is that the function is approaching the parabola this time. And can you write down the equation for this? Well, it could be similar, but this 2x plus 5 will be replaced by the equation of the parabola, right? Plus something else, correct? Plus something else, where the denominator should be x squared, not x squared, right? Since it's kind of a parabola which is being approached. So, well, it's kind of complicated to give you equation directly from here, but I hope you understand, right? X squared will work. So if you try to sketch a graph of, let us say n of x, correct? And this time, let me write down equation as of some parabola, which is this parabola, for example. So we could write this as, let us say x squared minus 1. That means the parabola has been shifted down, and plus 1 over the function here is, let us say, something, right? It could be 1 over x also. If I write 1, it could be that also. It doesn't matter. So here also, you will approach, no, that there should be 2 degrees higher than this. So what we will do is, okay, multiply this by x. Kind of. Let me do that. So it should be, it will get to that. Okay. So what I'm trying to say here is that when you do it, it is already 2 degrees. When I take common denominators, it will be cube. So that works. So this is it. This is correct. So our function, which is 1 over x, if x is very large, 1 over x becomes smaller and smaller, and it will approach x squared minus 1, which is parabola. So sometimes the asymptotes could be such that their end behavior is approaching parabola. So there we say that they are oblique to a second degree function, correct? Well, that gives you a wide variety of graphs which you are going to get across when you sketch graph for rational function. It also gives you an idea of how to write a rational function given the equation, given the graph. So we'll do all that in this exercise. I hope it really helps you to understand what we're trying to do. I'm Anil Kumar. You can subscribe to my videos and learn a lot. Thank you and all the best.